So hi everyone. Today actually we are going to take an extra class. This class is more focused on solving different types of problems. So it's not necessarily MCQ type of problem. It's like different types of like numerical problems, or we have to prove some mathematical expression, something like that. But the main goal is to to understand like different concept of different aspect of this topic of thermal physics by solving these problems. Okay. So anyway, this problem will be helpful to in order to deal with MCQ problems also. So let's start. So problem one. Normally insulated vessel 1 and 2 are filled with air. They are connected via short tube with a one. And the volume of the vessel and the pressure and temperature of air, the volume of the vessel and the pressure and temperature of air in them are P1, P1 and T1 and B2, B2 and T2. Okay. This is the volume of the vessel, and inside the vessel, what is the pressure of the gas? Of vessel one is P1 and vessel two is P2. Similarly, temperature is T1 per vessel one and T2 per vessel two. Okay. Respectively. Calculate the air temperature and pressure if okay. Calculate the pressure E and temperature T established after opening of valve B, after opening of valve. Okay. So it's the problem looks like this. So initially these are the two vessel. This is vessel one and this is vessel two. Each vessel, two of the vessels are connected by a valve. Okay. And initially the valve is shut down. So that means the pressure inside pressure, volume and temperature inside the valve 1 is P1, P1 and T1, and inside valve 2 is P2, V2 and T2. Okay. Now when you remove this remove the valve, I mean valve inside this tube. Okay. in that case, what will happen? Both these two gas will be mixed with each other, right? So in that case, for the total mixture, you have to calculate what is the pressure and temperature. Okay. So so initially for vessel one, so we also considered that the gas is following the ideal gas equation. Okay. So for vessel one, that means the equation will be V1 equal to N1 RT1, and for vessel 2 it will be V2 equal to NR T2, right? That means N1 is V1 by RT1 and N2 is V2 by RT2, correct? Now when two vessels are connected, when two vessels are connected, in that case the total pressure would be, let's suppose it's P, and total volume, let's suppose it's V, and temperature, let's suppose it's T for the whole mixture. So in that case the gas equation will be PV equal to nRT. Okay. Now here V is simply V1 plus V2, right? Because volume is the extensive quantity, you know. So the volume, we just add up the two volumes that are like that the volume that is available to the gas. So add those two volume, that gives you the total volume. Similarly, the number of moles is also extensive property. So N will be equal to N1 plus N2. You have to just add the respective mole for vessel 1 and vessel 2, right? So in that case, this will be the gas equation. Now we have to find out what is the uh, pressure and the temperature. So in order to find the temperature, we will take the help of the energy of the system. Okay. So since it's a 3D system, so from the total energy of the mixture would be energy of vessel 1 plus energy of vessel 2. So for total mixture, you know, 3 by 2. So we are taking three dimension system, so there will be 3 term multiplied. 3 by 2 half into mole, that is N plus kT, right? And this would be 3 by 2 N1 kT, kT1, and 3 by 2 N2 kT2, right? So here, so from here N, we know N is equal to N1 plus N2, so T would be equal to N1 kT1 plus N2 kT2 by Nk, right? So Kk will cancel, so it will become N1 T1 plus N2 T2 plus N1 plus N2. Now N1 and N2 can write it like this: P1 by T1, P2 by T2. So we'll substitute like this. So T will in that case T will become P1 by R T1 into T1 plus P2 V2 R T2 into T2 by V1 by T1 RT1 plus P2 V2 by RT2. So the equation will become T1 into T2 into P1 V1 plus P2 V2 by V1 T1 plus P2 V2 T2. Okay. This is the total temperature. Okay, so we got this. Now after getting the temperature of the composite system, now from this, using this equation of gas, we can calculate the total pressure. Okay, the pressure of the mixed system. So PV equal to nRT. So P will be nR by V, and T expression you know is simply T1 into T2 V1 into P2 V2 by P1 T1 plus P2 V2 T2. This will be the expression of the pressure. Okay. So this is how you have to solve this problem. So like using the properties of intensive variable and extensive variables and using the equation of gas, you can basically write the pressure and temperature of a system before mixing and after mixing. Okay. Now the second question is, gas consists of molecules of mass m and is at a temperature T in 3D, making use of Maxwell velocity distribution function, the corresponding definition of the corresponding distribution, so corresponding distribution of the molecules over kinetic energy E is given by options are option A. So basically you have to convert the Maxwell's velocity equation, the distribution of Maxwell velocity distribution in terms of Maxwell energy distribution. Okay. So there are four options are given. So E D equal to, first option is pi into 1 by I kBT to the power 3 by 2 to the power minus C by kBT into D. Option B is 2 pi 1 by pi kBT to the power 3 by 2 to the power minus E kBT turned into D. Option C is pi 1 by pi kBT 3 by 2 to the power minus C kBT ED, and option D is 2 pi into 1 by pi kBT 3 by 2 to the power minus C by kBT ED. Okay. These are the options given, so we have to evaluate. So we know that velocity distribution is this is the formula F3 into, in 3D the Maxwell velocity distribution looks like this: F equal to m by 2 pi kBT to the power 3 by 2 to the power minus m b square by 2 kBT into 4 pi d square dV. Right? This is the general Maxwell velocity distribution for 3D, the particle moving in 3D. So now, what we'll do next? Now we have to convert this variable from velocity to the energy. So kinetic energy you can write in terms of velocity. So E equal to half mv squared. So in that case V is 2E by m. and write it like this. Now, uh, so from here itself, we have to also use the integral form. The integral form is d equal to mv dv, right? So we can substitute here, so it will become m into 2e by m into dv equal to 2em dv. G equal to 2em dv. Okay. Now from here, so you just have to substitute this all this terminology here. So if E will become m by 2 pi abt the part 3 by 2. Mb square we can write it as 2e by abt, and 4 pi v square dv. So 4 pi v square we can write it as 2e by m, and dv we can write it as 1 by root under 2e by m, right here. Yeah, it's fine. Now, so from here, what we can do, if e equal to m by 5 it will cancel, so 2 to the power e by kbt, and this term will become 4 pi into 2 into uh, e by, so it will become into e into m to the power 3 by 2, right? And so 4 into pi also we can write it as 2 into root 2, so you can write it as to the power 3 by 2 into 2, right? So that means so 2 to the power 3 by 2, also here also there is a 2 to the power 3 by 2, and here also m to the power 3 by 2 is there in the denominator. So this 2 to the power 3 by 2 will cancel each other, and m to the power 3 by 2 also cancel each other, right? So in that case, Fe will become only one 2 will survive, right? M by pi abt to the power 3 by 2 into to the power minus c by abt into there's a pi is also here into root t, right? Root t g into k is also there. So the correct option will be option B. Okay. Similarly, if someone asked to write this distribution in terms of momentum, that is also an easy job, not difficult. The recipe is quite same. So you can write the energy half mv square, right? Also you can write T equal to mv, right? So that means V would be half mv square would be e square by 2m. So in that case, e square would be m square by v square, right? Or d equal to mv. This is the momentum basically. So dp would be m dv, right? So now in that case, the energy, the Maxwell distribution will become so AB equal to M by 2 by 2 B power minus M B square equal to T by V dB. So if P will now become so e to the power minus mb square, so mb. So this will this factor at the front will remain as it is, and this e to the power pound, so mv square is there. So we can multiply m one at numerator, one at denominator. So the upper term will be m square v square, the numerator. You can write an m square v square as p square, and the denominator will be 2m kbt. And 2mv dv, right? mv dv. So 2m dv, m dv you can write it directly as dp, and this v thing you can write it as m by p, right? Sorry, p by m. Sorry, it's p by m. P by m. There is also another term since it's 3dl. So it's v square d. Sorry, 4 pi v square d. 4 pi v square d. So in that case, it will become 4 pi b square will become p by m whole square, and dv will become m dv. dv by m, dp by m. Okay. Now that's simple. It's already done. So p will become m by 2 pi kbt. It becomes 3 by 2. It will become 4 pi p square dp by m cube. Okay. And more simplified actually. You can cut the m. That is, it will become 1 by 10 pi kbt into 4 pi p square dp. Oh, utility part term is also there. It will become minus p square qn kbt. Now the next problem is 3. In the case of ideal gas gaseous in 3D, the temperature at which the velocities of the molecules V1 meter per second and V2 meter per second are associated with equal values of the Maxwell distribution function. Maxwell distribution function if we okay. So basically in 3D. So at which temperature you have to calculate for the, if one type of particle is having velocity v1 and one type of particles have velocity v2. In which case, at which temperature both of their distribution will become equal. Okay. Yeah. So the temperatures were the correct and the options are given. So A is T equal to m into v2 square minus v1 square by 4 kb ln v2 by v1. Option B is T equal to m v2 square minus v1 square by 4 kb ln v2 by v1. Option C is T equal to m v2 square minus v1 square by 4 kb ln v1 by v2, and option D is T equal to m v2 square plus v1 square divided by 4 kb ln v1 by v2. So distribution in 3D looks like this: m by 2 kbt divided by 3 by 2 to the power minus m v by 2 kbt 4 by v square. So at a particular temperature T, their distribution, their V1 and V2 distributions are same, right? That means F V1 will be equal to F V2, right? So it will become m by 2 pi kbt equal to 3 by 2 into to the power minus m v1 square by 2 kbt 4 pi v1 square will equal to m 2 pi kbt to the power 3 by 2 equal to the minus m v2 square by kb 2 kbt into 4 pi v2 square, right? Now, so if we cut this part, now it will become v1 square by v2 square will be equal to e to the power minus m. So here also v, so this will become this side, so e to the power minus m v2 square by 2 kbt plus this exponential will go to the denominator. So in the bottom part of this expression, so it will become n v1 square by 2 kbt, right? So it will now become e to the power n kbt into v1 square minus v2 square, right? So v1 square by v2 square. If you take the log in both sides, so now ln 2 ln v1 by v2. So we take the exponent of this function in front. Since we are taking logs, we can take the exponent part as a multiplication, right? Now this part will become m by kbt into v1 square minus v2 square. So now t will become m into v2 v1. So in the answer it's written v2 they have written in front, so v2 square minus v1 square, and to compensate that the negative term, we can write the ln as opposite ln, like invert. Okay, invert this expression inside the ln, right? So B2 minus B1, right? In that case, a negative sign will appear as a multiplied with the normal. Okay. So T is now this. So what T is this is the correct answer, right? So the correct answer will be so in the denominator B2 by B2 is the option B2 square. Okay, this one there is a plus sign. So the correct option is option B. Okay, the next problem is the work performed by one mole of vendor was gas during its isothermal expansion from the volume V1 to V2 at temperature T is given by A T log V2 minus B U minus B plus A into V2 minus V1. Option B RT log V2 minus B V1 minus B plus A 1 by B1 minus 1 by B2. Option C is R2 log B1 minus B V2 minus B plus A into 1 by B1 minus 1 by B2. And option D is R3 log B2 minus B1 minus B by B2 minus B plus A into 1 by B2 minus 1 by B2. Okay. These are all the options are given. So now, the problem says it's a van der Waals gas, and it's an isothermal expansion, right? Okay. So isothermal expansion means D equal to dq plus dw. So dw is pdv. So wow. Okay. So we know dw. So, dw equal to pdv. So w will be equal to integration pdv. So it's a van der Waals gas. Van der Waals gas equation, you know, E plus E by d square into V minus B equal to RT. Now to write P in terms of V, since we're integrating with respect to the volume, right? So P would be RT V minus B minus A by V square. So now substitute the expression of P here. After that, we get RT by V minus B minus A by V square dV. Okay. So the integration limits are what is the V1 to V2, right? These are the integration limits. So the first time if you do the integration, so it gives you the one by V term, so it's just ln. It gives the ln, so RT into ln V2 minus B by V1 minus V2. Similarly, next time if you do the logarithm, means it will become A 1 by V2 minus 1 by V2. Okay. So the this is the correct expression of the work done. The correct option is option V2 minus V1 minus V2. So option A. The option is the correct answer. uh, equation of state is given by equation of state of a gas is given equal to RT B minus B into exponential minus a RTV. In that case, then the critical volume and critical temperature have to calculate them. Calculate critical volume and critical temperature. So in a PV diagram, the condition for a critical point in the PV diagram is given by these two conditions, right? Del P. So the critical conditions. These are the two conditions of del P, del B at constant equal to 0, and del square P, del square B at constant T also equal to 0. These are the two conditions. So now it's meant, so the gas equation is this. So let's first start with this first conditions. Okay, so if you substitute the gas equation in the first conditions, before that let's simplify the expression a bit. So instead of P, let's take ln P. Okay, ln P, so there will be no exponential term, so the calculation will be pretty easier. So ln P will be ln RT minus ln B minus B minus A by RTB. Okay. So now if you take the derivative, so del P of ln P. See, del P del B is equal to 0. Del ln P del B is also equal to 0, because del ln P del B is nothing but 1 by P del P del B, right? So that since del P del B is 0, so this term will also be equal to 0, right? So so you can take this also as 0, right? So this would be simply, so 1 by RT is 0. So the second term will be minus 1 by B minus B, take the derivative of ln, plus A by RT B square, right? Since B is in inverse, so this will be equal to 0. Now it will become A RT by B square will be equal to 1 by B minus B. Now from the second condition, it comes like this. Second condition, okay, so second condition is del square del B square into ln of P, right? So it's two derivatives. So if you do two derivatives, so in that case it will become 1 by B minus B. So first derivative we know, this is the first derivative. So del B of minus 1 by B minus B plus A by RT B square is equal to 0. It will become so the minus will become plus B minus B whole square will be equal to, so you get minus, which will go this side, so 2A RT by B cube. Okay, yeah. Now from here, from this equation, you know, RT is nothing but A into B minus B by B square. So if you substitute this RT here, in that case, the whole thing will become 1 by B minus B whole square into equal to 2A by A into B minus B by B square. This thing is whole cube. Sorry, not whole cube. This thing is just RT into V cube. Now if we simplify the things a bit, it will become 1 by B minus B whole square will be equal to 2 is there in a numerator, 2 by B into B minus B. Okay. Now from here, So what you can do from here, you can cancel v by v from here. So 1 by v minus b equal to 1 2 by v. To solve this, you will get v as 2v. Since v is nothing but vc, that is the critical volume. Okay. So since you got vc, so it's easy to get tc. Okay, tc also. Tc also you can easily get from using this relation. Just substitute the vc here. It gives you RTC equal to A into VC minus B by VC square. So TC will become, if you substitute VC here, so A into VC is 2B minus B, VC square 2B squared by R. So that gives you A by 4RB. Okay. TC is A by 4RB. Okay. See, now you have to solve this problem. So you have to take the conditions, compare those two conditions, and from there itself you can get the critical point. So next is find the maximum attainable temperature of ideal gas in each process, of ideal gas in each process given by T equal to T naught minus alpha T square, where P naught, alpha and beta are positive constants, and V is the volume of 1 mole of gas. V is the volume of 1 mole of gas. Okay. So now let's write the equation. So we know PV equal to nRT. You already knew it. So we have to calculate the maximum attainable pressure. So we have to put the maximum attainable temperature. Okay. So you have to write the temperature in terms of the other variables, and from there we have to take the derivative with respect to the volume, and that we have to compare it equal to 0. That is basically the condition for any extremum condition, right? So let's do it. So T, you can write P by V by NR. So P we know P is P naught minus alpha V square into V by NR, right? This is the expression of the temperature. Now I have to find for which value of okay, so for like what is the value of extremum temperature? Okay. That means you have to take the temperature, since the temperature is written in terms of volume, so del T del V, we have to put it equal to 0, and from there if you do the derivative, the first will become T naught by R minus 3 alpha if you take the derivative. So D2 is there, so 3 alpha into V square by R. Okay, and cancel, yeah, this will be equal to 0. Now from here, V would be root under P naught by 3 alpha. So that means for V equal to P naught by 3 alpha, the temperature will be maximum. So now, to calculate the temperature, what I have to do? It's just substitute this volume expression into the expression of the temperature. So Tmax would be uh, T naught by nr minus alpha by nr into T naught by 3 alpha or 3 by 2, right? So from here, if you take there is something in this. So alpha will be cancelled. P naught will also cancel. So if you uh, simplify this expression, it will become 3 mass will become 2 by 3 into P naught into P naught 3 alpha, right? And this will be the correct expression. Find the isothermal transmissibility alpha of an van der Waals gas as a function of volume V and temperature T. So for van der Waals gas, you have to find the alpha. Alpha we know is the isothermal compressibility expression. In differential format is 1 by V into del P at constant T. Okay. So now we have to compute first. That means what is del P by del B, right? So or del P by del P, whatever the way you want. So the first write the van der Waals equation. So van der Waals equation is this basically P plus A by V squared into V minus B equal to R, right? Now from here, since T is just a constant isothermal process, so if you take the derivative both sides, it will give you the right hand side will be equal to 0, we know. So left hand side gives you dP minus A by B cube dV into V minus B. If you take the first as a constant, and give you the second one, it will give you P plus A by B squared into dV. This is equal to 0. Now just divide the whole thing by dV. In that case, it gives you dP by dV minus A by B cube into V minus B plus P plus A by V square is equal to 0. Now from here, you can write dP by dV like this. dP by dV is equal to minus P plus A by B square into D minus B plus A by B cube. So if you further simplify it, it will become P cube into V minus B minus PV cube plus AB plus A into V minus B. A into V minus B. So this is the expression of dP dV at constant temperature. Since we take the temperature as constant, because that's why the right hand side is equal to 0. So we got the expression of dP by dV, right? So just take the inverse of it, so that gives you dV by dP, and put that thing into the expression of this alpha. Okay, so after doing that, you will get alpha equal to minus 1 by V. So taking the inverse, it will be B cube into B minus B. This thing is numerator, denominator minus P V cube plus A into V plus A into V minus B. Okay, so VB will cancel, so denominator will V square is a term that will remain. So and you can also absorb the negative sign into the denominator. So it will be to B squared B minus B by PV cube minus AB plus A into B minus B. Sorry, this is B minus B. Sorry, B minus B. Since we absorb the negative sign into the denominator. Okay, so this is the expression of what is this called? It's alpha term. Okay. Okay. Now the question 8. N mole of certain ideal gas at temperature T0 where cooled isotorically so that the gas pressure reduced in time. So then as a result, the isobaric process, the result of the isobaric process, the gas expanded till its temperature get back to initial value. Find the total amount of heat absorbed by the gas in the process. Find the total amount of heat absorbed by the process. Okay. So it's the whole process is looks like this. So initially it was P0, V0 and T0. Now from here, it basically pressure remains same. Sorry, the volume remains same. So it Isochorical process, so it basically compressed, so volume remain constant but the pressure reduced, so it's an isochoric process. So isochoric, and also its temperature is also got changed, so both pressure and temperature got changed, volume kept constant. So P naught becomes P naught by N, volume remains same, and temperature becomes TV, that we don't mention. Okay. Then from there it again get back to its initial temperature, that is T0, but this is a so this is a isobaric process. So no, sorry, yeah, it's a isobaric process. So temperature got to T0 to its initial value. Now pressure remains same, T0 by N, but the volume changed to some volume, let's say Vc. Okay. So in this case, we have to find the total heat that is absorbed during this whole process. Okay. So for that, we have to first calculate what are the unknown, like this unknown temperature and unknown volumes that are involved in this process. Okay. Okay. So have to first find out those quantities. Okay. So let's do that. So to find that, we use this ideal gas equation. Okay. So yeah. So from first it is P naught V naught by T naught is equal to V naught by N into V naught by TB. So that means TB is T naught by N. Okay. So similarly from here to here, this is the thing, from here to here it is uh, P naught by N into V naught by TB equal to P naught by N into Vc by T naught. So TB we know, TB is T naught by N we know, so P naught by N, P naught by N will cancel, so V naught by T naught by N equal to Vc by T naught. So the Vc will become N into V0. Okay. So for the first process from, so let's suppose 1, 2 to 3. So during the process from 1 to 2, since it's an isochoric process, so heat is only related to the temperature change, not the work done. So dT equal to du plus dw, right? So du is dw is basically 0. Here dw is 0. dq is du, that is cv dt, right? So ncv, temperature change is from T0 to T naught by N, right? So T naught by N by minus T0. Now from process 2 to 3, two things are happening. Both the temperature gets changed and also the volume gets changed. So dq will become du plus dw. So du is cv dt, ncv dt, right? ncv dt, and dw is pdv, and pdv also you can write it as nr dt, right? Since it's an ideal gas. So ncv dt is ncv, so t change from so tv is basically t naught by n, so t naught by n to t naught, right? So t naught minus t naught by n. Next is the so also the temperature change nr equal to dt, so it will also, so volume change we are writing actually in terms of temperature, so it will also become t naught minus t naught by n. And if we just so now the total dq total would be the addition of all these three, ncv t naught n minus t naught plus ncv t naught minus t naught n plus nr T naught minus T naught. Okay. So now these two terms will cancel. So just only this NR term will remain. So NR into, you take T naught as common, so it will be 1 minus 1 by N. This is the due Q total. and of an ideal gas is written through the cyclic process ABCA as shown in figure. So I'll draw the figure. It absorb 50 joule of heat during part AB, no heat in part BC, reject 70 joule heat during CA, and 40 joule work done has also been done, work done during BC. Okay, so during BC, although there is no heat involved, heat transfer is involved, but the system is doing some work, 40 joule of work during BC. Okay. So two questions are asked. The question is, find the internal energy of the gas at B and C if it is 1500 joule a day. So find the internal energy at B and C if it is 1500 joule at A. And option second question is, calculate the work done by gas during C. Okay. Okay, so before that, let me just draw how the PV diagram looks like. So the PV diagram looks like this. Okay. PV diagram looks like this. PV. C A B. Okay. So first let's take from A to B. Okay. So from A to B, what is happening from A to B? 50 joule of heat is absorbed from A to B. So delta Q. So from A to B. Okay. So from A to B, fine. So A to B is heat is involved, but there is no work done. Okay. So du equal to only dq, right? So dq is 40 joule. So so u at B minus u at A is equal to 40 joule. Now u at A is already mentioned. So it's not 40, it's 50 joule. It's 50 joule. It's 50 joule. Now u at B you have to calculate actually. Okay, so yeah, find the internal energy at B and C. So UB would be simply 50 plus UA. UA is already 1500 mentioned, so 1550 joule. That is the internal energy at the point B. Now to find the C, so C here you can see this is basically adiabatic process is happening here. Okay. No, sorry, it's not adiabatic. It's heat during with no heat during BC. Yeah, no heat during BC. That means it's a adiabatic process here. So from B to C, du we know. So dq is du equal to du plus dw, right? So here dw is minus 40 joules. So du equal to minus dw. So minus dw is 40 joules. This will become plus 40, right? Du is basically so B to C it's moving, right? So from B to C it's happening. This dq is 0 from B to C, you know, since it's a adiabatic process. So du would be uc minus ub equal to 40. So uc would be 40 plus ub, you know, 1550. So it will be uc would be 1590. Okay. So uc and ub have calculated the internal energy at B and C. Now next thing is calculate the work done during the process CA. Okay. So in that case, uh, the work done have to calculate. Work done, we know dq equal to du plus dw. So dw is basically dq minus du. So during this CA process, the dq is 4 joule, 40 joule, right? So 40 joule minus du is basically from C to A. So u A minus u C. So 40 joule minus u A is 1500 something. It's yeah, 1500. 1500 minus 1590. So okay, this is rejected. Is 70 joule of the 70, 70, 70, 70. 70 joule is rejected. Okay, so rejected means this would be minus. So minus 70 plus 90 will be 20 joule. DW is 20. So the total work done is during the process CA. This is happening at CA. Yeah. So total work done during CA is 20 joule. Okay. Uh, so now we take the next problem. So question 10. Carnot engine A and B are operated in series. The first one, A, receives heat at 900 Kelvin, receives heat at 900 Kelvin and rejects at T Kelvin reservoir. Okay. So the second engine is connected in a series way to the first engine. Okay, so the reservoir for the first engine would be the source for the second engine, right? So the second engine receives the heat rejected by the first engine. That means it receives from T Kelvin. So receives from T Kelvin or the heat rejected by engine input and then rejects to heat reservoir at 400 Kelvin. This is a statement. Now the two things you have to find out. Okay. So the first thing that you have to find out is so yeah. So two situations are given. So for these two situations, you have to find out what is the value of T. Okay. So calculate the T. So for two situations, for given situations, situation A is the work output of the two engines are equal, and B condition is the efficiency of the two engines are equal. Okay, so for these two cases, you have to calculate the situations, you can say. So first case is the the efficiency is equal. So okay, sorry, the worked outputs are equal. So what is the work done for machine A? So it's basically how the machine is working. So it's pulling heat from a reservoir where it's T1, it's at 900 Kelvin, and it pulled the heat and dump it into a reservoir with unknown temperature T that you have to find out. And the second reservoir is second engine is taking the reservoir of the first engine as a heat source. From here it is like after taking the heat, it dumps it into the reservoir of temperature T2 equal to 400 Kelvin. Okay. This is engine 1, this is engine 2. Okay. Now let's suppose it's draw Q1 heat and it pulls up Q heat here. Now from here it take Q heat and again it dumps Q2 heat from here. Okay. So for this case the work done is Q1 minus Q, and for this case the work done is W1, W2 is Q minus Q2, right? So so the work done is equal, so it's the first according to the first situation. So that means W1 work done 1 is equal to W2. So this becomes Q1 minus Q equal to Q minus Q2. So if we simplify it, it will become Q1 minus Q2 by Q equal to 2. Now since it's an Carnot engine, or it can, so that means it Q1 by Q is basically T1 by T, and Q2 by Q is equal to T2 by T, right? So this means you can write it like sorry, it's Q1 plus Q2. Q1 plus Q2. So T1 plus T2. So it will become T1 plus T2 by T2. So yeah, so it will be equal to 2. So T would be 2. So T would be T1 plus T2 by 2. So that means T1, T2 we already know T1 is 400 and T1 is 900, T2 is 400. So 900 plus 400 by 2, this gives you 650 Kelvin. Okay. So the temperature of this intermediate reservoir, that's the temperature is 650 Kelvin. Okay. So this is the answer for the first situation. Now the second situation, what it is telling? The efficiency of two engines are equal. Okay, so first case was the work done was equal. Now the second case the efficiency is equal. So the efficiency formula we know is eta is basically for the Carnot engine is 1 by so for first engine eta 1 is 1 by T by T1, and for second engine eta 2 is 1 minus T2 by T1. Okay. So since the efficiencies are equal, so eta 1 will be equal to eta 2. So in that case, it will be 1 minus T by T1 is equal to 1 minus T2 by T. So T square will become T1 plus T2. T is basically T1 into T2 square root. So for the second case, the temperature is under T1 by T2. If you multiply 400 into 900, it gives you 4 into 9, 36. So it gives you 600 Kelvin. Okay. Now we go to the question 11. Uh, Mass of liquid at temperature T1 is mixed with an equal mass of same liquid T2 at lower temperature. So T2 is less than T1. Okay. The system is thermally insulated. So that means there is basically no heat transfer with the environment. Okay, since it's insulated. So you have to find out, compute the entropy change. Okay, so you have to compute the change in the entropy. So for that, okay. So So if you mixed if you mixed to liquid temperature T1 and T2, in that case, you have to, when this mixture comes to a thermal equilibrium, in that case, the equilibrium temperature you have to first find out, right? So the first case, so the heat, that means the heat that is rejected by the hot liquid, uh, the same heat will be absorbed by the cold liquid, right? So uh, so the heat rejected by the hot liquid is MC T1 minus T. So hot liquid cools down from T1 to T, and during that process, this is the amount of heat that it would release, and this same amount of heat will be absorbed by the cold fluid, and its temperature will rise up. So that heat would be MC T minus T2. So both the heat would be equal in each other, right? Now the C is same and M is same because in the question it's mentioned both types of liquids are same nature and their mass is also equal. That's why MC are equal. So uh, T is then T1 plus T2 by 2. So this is the final temperature. Okay, so this is the final temperature of the mixture. Okay, so in the question it's mentioned to calculate the change in the entropy. Okay, so yeah, so entropy change formula, you know, delta S is dq by T. This is the change in entropy formula. So, uh, so for the liquid one, delta S1 is change in entropy is dq we know is mc dt by T. For liquid one, the temperature is basically decreasing, so T1 to T. So mc ln, do the integration ln T by T1. Similarly for liquid 2, it's delta S2. The temperature change from T2 to T. So mc dt by T, so it will be mc ln T by T2. So total change in entropy would be delta S equal to delta S1 plus delta S2. So MC ln T by T1 plus MC ln T by T2. Now you can write this addition of two ln as a multiplication inside the ln. So MC into ln T square by T1, sorry, T square by T1 into T2, right? So now from here, delta S equal to MC ln. So T square will become T1 plus T2 by 2, and this this whole thing you can write as a square by just making T1 into T2 into square root of T1 into T2. Okay. Now from here will become 2MC ln T1 plus T2 by 2 over T1 into T2. Okay. So this is the total entropy change of the system. Now we know that any kind of spontaneous process that is happening into the nature, for all those processes, the change in entropy should be always positive, right? Now for this case also, since like this is the total change in entropy for the whole system. If you check here, the first term in the denominator, you see it's arithmetic mean of two numbers T1 plus T2, and this is the geometric mean. Okay, A for T1 and T2, and this is the geometric mean of T1 and T2. Okay. Now we always know that AM, arithmetic mean of two numbers, is always greater than geometric mean. Okay. So that means delta S total is always greater than 0. That is expected. Okay. For any kind of spontaneous process that is happening in the nature. Okay. So in this case also, its delta S is always equal to 0, okay, which is consistent with the physics. So Now the next problem is question 12. A Carnot engine has efficiency of 1 by 6 on reducing the sink temperature by 65 degrees centigrade. The efficiency become 1 by third. Okay. The source temperature is given by, so the source temperature to find out the source temperature is given by how much degree? Sorry, just degree. Okay. So the initially the efficiency is given by 1 by 6. So initially eta is 1 by 6. That means 1 minus T2 by T1 is equal to 1 by 6. Now for the second case where the efficiency become 1 by third, where the sink's temperature is increased by sink's temperature is reduced by 65 degrees. Okay. The source temperature, so source temperature we have to find out. So from here you can write T2 is 5 by 6 of T1. Okay. Now for the second case where eta is 1 by 3, in that case the temperature of the source, let's take it as T2 prime, and sink is T1. Okay. T1 prime, let's say. Okay, then T2 prime is nothing but original T2 that we had, that is reduced by 65 degree. Okay. And T1 prime we have to find out. Okay. No, T1, no, sorry, T1 is remain as it is. So only T2 is decreased. T1 will remain same. T1 is remain same. Source is remain same. Sink temperature is only get reduced. Okay. So 1 by 3 would be 1 minus T2 by T1 minus 65 degree by T1. That is equal to 1 by 3 equal to 1 minus T2 by T1 is 5 by 6 minus 65 by T1. So from here if you do 65 by T1 is equal to 1 by 3 minus 5 by 6. So it will become 1 into 3 by 6. So it will become 1 by 6 here. So T1 will become 65 into 6, that is 390 degrees centigrade. Can you calculate also tell me? T1 will be 390 plus 273 Kelvin. Okay, so now goes to the next problem. So question 13. An ideal gas expanded adiabatically from B1 to B2, then it's compressed isobarically to P2, P1. Finally, the pressure is increased to P1 at constant V volume, constant V1, volume V1, then which of the following is correct? Okay. There are certain information given, so to find out which of them is correct and which of them is wrong. The work done during this process is the work done equal to 1 by 1 minus gamma into V2 V2 by minus V1 plus V2 V2 minus V1. Option B, statement B is heat will absorb in isoporic process. And option C is statement C is the efficiency of the cycle. Eta is 1 minus gamma V2 by V1 minus 1 divided by V1 by V2 minus 1. First, let's draw the diagram. How it looks like. So from its move adiabatically from P1 to P2 V2. Okay. So this was the A. This was the A. This was P1. So this is P and this is B. So it's P1 V1 to move adiabatically to A to B, B2, B2. Now from B, then it compressed to P2 V1, P2 V2 to P2 V1. Okay, so P2 V2 to P2 V1. From here, A B to C. This is P2 V1. It is compressed. Okay. Now finally, the pressure is increased P1 to P1 at constant value V1. So from here, it again moves to this. Okay, so its pressures got increased. So this is adiabatic process. Adiabatic. This is isobaric, and this is isopropyl. Okay. Now first what we have to find out is the total work done during this cycle. So I have to check whether according to the problem is it correct or not. whatever mentioned in the problem. So the first thing is like work done during the AB, we have to find out first. So AB we know this is a adiabatic process, right? So adiabatic process we know the work done formula is basically this one, 1 minus gamma E final into V final minus V initial into V initial, right? This was the work done expression for the case of an adiabatic process. Now here, which is 1 minus gamma E final, V final is P2, V2, yeah, P2, V2, and V initial means E1, E1. This is the work done for adiabatic phase. Okay. Talk to adiabatic. Okay. Now, so for the second case, so during B2C isobaric, so here also there will be work done. So W isobaric will be P2 into V1 minus V2. Okay. So these are the two work done. So that means total work done will be total work done will be 1 by 1 minus gamma P2 V2 minus P1 V1 plus P2 V1 minus V2. And in the problem it's mentioned V2 minus V1, so that means it's not correct. Okay. It's V1 minus V2. Okay. Next is the during the process CA whether there is heat absorbed is not. Isochoric means this CA process. Okay, this CA process. So during this CA process, you have to check whether the heat is absorbed or not. So you have to check. So during CA process, change the extending dq value is basically T CVDT, basically, sorry, CVDT, change in temperature. So CV is T1 minus T2. Okay. Now also we can yeah. Also you can write this CV uh, in terms of gamma also, right? So we know Cp minus Cv is equal to R and Cp by Cv is equal to gamma. So that means from here we can write as Cv equal to sorry, Cp equal to gamma into Cv, right? Now if you substitute this thing here, so it will become gamma Cv minus Cv equal to R. So Cv is equal to R minus R by gamma minus 1. So you have to substitute this thing here. Okay. That case dq will become R in R by gamma minus 1 into T1 minus T2. Yeah. So that means see, since the signs are all like signs are positive, so that means this heat is absorbed. Okay, so this means the second statement is correct. Okay. Or you can check it by in terms of volume also, gamma minus 1. R T1 is basically CV to minus T2, yeah. R T1 is V1 you can take common, so it will become minus P1. Okay. Sorry, P1 minus P1 minus P2. So P1 minus P2, you can see P1 is higher than P2. Okay. So that means this is P1, this is P2, this is P1. Right. So P1 is, since higher than P2 is P1 minus P2, this also term is also greater than 0. So in that case, d is greater than 0, so dt is absolute. So now we have to check the efficiency of the cycle. So efficiency of the cycle is given by eta is work done by it. So work done expression is this. One by one minus half of P2 V2 minus P1 P1 plus P2 into P1 minus P2 then divided by the Q. Q is this one. P1 gamma minus 1 P1 minus P2. This is the expression of the efficiency of the cycle. Now the next problem is prove that a Cp minus Cv is equal to T into del P del T at constant V and del V del T at constant V, and V is for van der Waals gas, prove Cp minus Cv is equal to R1 plus 2A REV. So to prove both of these things, quantities. Okay. So first let's start from Cp minus Cv. So Cp minus Cv is equal to del Q del T at constant V minus del Q del T at constant V. So this will become, so del Q is nothing but T into del S del T at constant V minus T into del S del T at constant V. Okay, Cp minus Cv. Now, so we now will use the identity from the functional form of the differential form of the entropy. So as we know, entropy is a function of temperature and volume. So total derivative ds is del S del T dt plus del S del V with constant V constantly dV. So ds dt at constant P pressure is equal to del S del T at constant V plus del S del V at constant V into del V del T at constant V. This identity you can use. So that means del S del T at constant V minus del S del T at constant V multiply T both the side, it will become T into del S del T T and del S del T at constant P equal to T into del S. So del S del B. Uh, Del S del V from Maxwell relation, you can write del S del V at constant T equal to del P del T at constant P. Okay. So del P del del S del P can write del P del T del T at constant V into del P del T at constant P. Okay. Okay. So now, so this thing is, these two things are nothing but Cp minus Cb. So that becomes T into del P del T at constant volume in del P del T at constant P. This thing we proved. Okay. So now it has been asked that for Maxwell, for Van der Waals gas, we have to find out this particular form of Cp minus Cv. Okay. So we will do that now. So for that, we need both the derivative of the pressure with respect to the time and derivative of volume with respect to temperature. Pressure derivative and volume derivative with respect to the temperature. So let's first write the equation of Van der Waals gas. So P plus A by B square into V minus B into R. Okay. First we will find del P del T. So write it like this: P plus A by B square into RT B minus B. Now from here, if we take derivative del P del T at constant B equal to R B minus B. So this way I got del P del T at constant B. One term we have already find out. So in order to find the next second term, what you can do, this was the equation. So you can take the derivative. So you can with respect to V. So derivative. Yeah. Now take the P as constant and take a derivative of V with respect to T. Okay. So that will give you, so first term del T of P plus A by B square into B minus B plus P plus A by B square into del T of B minus B equal to R. Okay. Now if you do the derivative, it will give you minus 2a dq B minus B plus E plus A by B square del B del T, then also del B del T here, also del B del T is equal to now if you simplify it more, it will become, to take del B del T as common, the whole term will become del B del T at constant T will be equal to R by B minus B, whole thing divided by RT into B minus B whole square minus 2a by B cube. Okay. So we got del P del T, we got del B del T. Okay. Now so substitute these two quantities here into the main expression Cp minus Cb. If you do that, so Cp minus Cb will become T into R into B minus B into R into B minus B divided by RT B minus B whole square minus 2a by 50. Okay. This will be the expression of Cp minus Cb. Now you can further simplify this thing. You can write it like this. You can cancel some of the terms. B minus B, you can see there are common terms. So you can further simplify it. So Cp minus Cp, you can write it as R by 1 minus mu by Vq into B minus V22 by RT, or Cp minus Cp equal to R into uh, if you take V as much greater than V, in that case you can write it as 1 minus 2a Vq into Vq RT, or R into 1 minus 2a by RT V inverse. So now if you, after binomial expansion of this particular equation, you can neglect the higher order. Okay, in that case it will become R into 1 plus 2a by RT V. And right, neglect in higher order. This is the expression of Cp minus Cp, whatever somewhere at that percent. So this is it. So this is our last problem. So today we'll end the class now. Okay.
Hello, hello, sir.
Yes.
Can you please read out just 1 to 9 question? I have just missed that question, that part.
What?
1 to 9 questions. I have just missed that part.
Yeah, one
Just
to nine. Na,
questions.
I'll upload it into the YouTube from where from there you can check it. Okay.
Oh, in the YouTube, na?
Yeah, yeah. The links are in
Okay,
the
okay,
YouTube. Right? You can find the link, right? They shared you the Google, like the link, like
okay,
where you can check all the YouTube videos, right?
okay, okay,
Yeah,
okay.
yeah.
In the swam portal, na?
Yeah, in the swam portal. Yeah.
Okay, okay. Thank you, sir.
Okay. Okay. Thanks.